Okay, this is a quick lesson on the speed of sound. I'm going to back it up. In the last lesson, Intro to Waves, we talked about parts of a wave, different examples of things that travel in waves, amplitude, period, frequency, all that good stuff. But we'll be looking now specifically at the speed of sound, which is a specific type of longitudinal wave, and yeah, how fast does it go? Well, the first thing to tell you is that it requires a medium to travel in, which means sound waves need something to vibrate, and in space, there's nothing. It needs matter. So, usually, the way that we're designed to make sounds and receive sounds is we vibrate all the air particles around us. Basically, the stiffer the material, the faster sound will be. So that means that speed of sound will be greatest in solids and least in gases. In general, if you're wondering why that is, it has to do with proximity and the way that those particles are bound to each other. So in the solid state, if you vibrate this particle, well, it's close and attached to all these other particles. So very quickly, you could get a vibration through the whole piece of matter. Whereas in a gaseous state, if you vibrate the air, let's say here, it does take more time to transfer from one particle to the next because of their spacing. For sound waves specifically, and specifically in air, there is a dependence on temperature. For sound waves traveling through air, this formula we're about to use is just for air. All right. The hotter it is, the greater the temperature, the faster sound is. So air particles move faster as the temperature increases, and as the temperature rises, so does the speed of sound based on this formula right here. So it goes v, that's velocity, equals 332 plus 0.6 meters per second per degree Celsius times the temperature in degrees Celsius. Now that looks very complicated, but it's just this. It's very, very easy to use this. V equals 332 plus 0.6 times the temperature. Temperature's in degrees Celsius. Speed's got to be in meters per second. And the 0.6, it just has these units here. So let's give it a shot. Given a summer day, it's 20 degrees Celsius at my place today, actually. Let's find the speed of sound. So you go V equals 332 plus 0.6 times the temperature, 20 degrees Celsius. So that can be punched into your calculator all in one shot. 332 plus 0.6 times 20 equals, and it gives you 344 meters per second. And you're not going to get a huge range here. Like the slowest sound we'll ever get is around 320 in air, and the highest it'll ever get might be around 360 or 370 if it's really hot. Well, here's a 30-degree day. If the air temperature is 30 degrees, you see lightning, and you hear the thunder roll in 3.21 seconds later, how far away is the lightning? So how far away, you just use the old formula V equals D over T. So distance equals speed times time. You have the time, it's 3.21 seconds, but you don't have the speed that the sound's traveling at. So we go to speed of sound equals 332 plus 0.6 times temperature, in this case, is 30 degrees Celsius. Type that into your calculator, 332 plus 0.6 times 30 degrees Celsius, and you get 350 meters per second even. And that got a little ugly, meters per second. So if I want to find that distance, now I just go 350 meters per second times 3.21 seconds. 350 times 3.21, it equals 1123.5, and that would be meters, or that would be 1.1 kilometers or kilometers. Another way to use it: on a given day, you find a tuning fork produces sound with a frequency of 512 hertz. That is a frequency, F, and a wavelength of 0.7. Find the temperature of the air. So now we're going to be using the formula to find temperature. V equals 332 plus 0.6 times the temperature. And now we're going to be solving for temperature. How we're going to find the speed of sound in this case is V equals frequency times wavelength. So that's 512. That's the universal wave equation from last lesson times 0.7 meters. So I go 512 times 0.7 equals 358. Ooh, this is going to be a hot day. 358.4 meters per second. So I'm going to sub that in, 358.4 meters per second equals 332 plus 0.6 times the temperature. Move the 332 over, so you go 358.4 minus 332 equals 0.6 times the temperature. I do that subtraction, 358.4 minus 332. I get 26.4. That's not the answer. That's equal to 0.6 times t. You got to divide out the 0.6. Got to divide out that 0.6. And I get 44 degrees Celsius. So that is hot. So you can see, that's about as hot as you're going to find it anywhere on Earth. And the speed of sound is just south of 360. So that's the way that goes. Now, when you're going really, really fast, like in let's say a fighter jet, and you can get close to the speed of sound, we use a different sort of number, and it's called a Mach number. Mach 1 is defined as the speed of sound at a given air temperature. So in that last example, Mach 1 would have been at 358. You're traveling at Mach 1 if you're going 358. The example before that, you would say Mach 1 was 344. Anyways, so if you're traveling at greater than Mach 1, you're said to be supersonic. So supersonic, super means greater than, so supersonic, greater than the sound, greater than the speed of sound. Subsonic is below Mach 1, and then above Mach 5 is deemed hypersonic. So those are just three terms for you. We're not going to do a test on this chapter or an assessment or whatever you want to call it, but I would usually put terms like this and sprinkle them into the multiple choice. See if you guys knew your stuff. So to find the Mach number, you're flying your airplane at 839 meters per second. The temperature is 6 degrees Celsius up there. What is your Mach number? So first advice I can give you, now I know we don't have an exam this year, but I will tell you that the 6 degrees Celsius, if you see a temperature in the sound unit, then even if you're completely lost, you can be darn sure that this is something that you're going to have to do. 6 degrees Celsius. So even if you have no idea what else to do, this formula should be on your formula sheet. Just do this. Do the speed of sound formula, 335.6 meters per second. And then you've actually got about half the question done here. Like this person, if you did anything else whatsoever that made sense, you'd get 2 out of 4. So the Mach number doesn't really have a formula per se, but it's your speed over the speed of sound. So your speed is 839 meters per second, and the speed of sound on this day is 335.6 meters per second. And it looks like that'll give you a Mach number of 2 point something. Let's see, 839 divided by 335.6. And it's Mach 2.5. There's no units on that. It's a Mach number. It means you're traveling at 2.5 times the speed of sound. Converting the Mach number to a speed, if a fighter jet flies at Mach 3.2, 2 degrees Celsius, what's the plane speed? So again, air temperature. Even if you're completely lost, do this. 2 degrees Celsius. So we go 332 plus 0.6 times 2 degrees Celsius, and it gives me 333.2 meters per second. So if your Mach number is 3.2, then to find your Mach number, all you got to do is multiply that by that speed of sound. 3.2 times the speed of sound. Speed of sound is this. So I go 3.2 times 333, and I get 1066. Well, that's not the Mach number, that's the plane speed, sorry. Plane's speed is equal to 3.2 times 333, 1066.24 meters per second. Or we could round that for 2 digits to be 1100 meters per second if you prefer. So that is a quick kind of crash course on speed of sound. It's the normal lesson that I do, other than I ramble on a little bit about this and that. Let me go over here to our Google Classroom and just show you what you're up against in terms of your assignment today, speed of sound. I think I only have you doing a couple. I actually forget exactly which ones I'm having you do. 35 is one of them. I know that. There's just a few of them, like 3 of them. It shouldn't take you hardly any time at all, and you can have this done in just with looking at this and making sense of it. Oh, there it is right there, number 35, 36, and 37. So let's open that back up. 35, 36, and 37. So 35 is just inputting those temperatures and finding the speed of sound. There's one with the 90 kilohertz, find the wavelength. That's like that example we did with the tuning fork. Kilohertz means 1,000 hertz, so that's 90,000 hertz. And then 37 is a storm question. How far away is the storm? That's exactly like that thunderstorm question that we did as an example, okay? So I don't anticipate you're going to have any issues whatsoever with this, but if you do, leave it in the comments as usual, or you can email me also through Classroom, and I'll get back to you as soon as I can. And we're almost to the end of the course here, guys. So what else do I have to do? Oh yeah, I got to sign off. All right, good luck, guys. Keep the emails coming if you have questions.